Hello, everyone. My name is Donghang, and I'm a research scientist at TikTok. And today I want to share one of our ongoing research projects about trustless attestation verification. So we want to use this to provide more transparency when we use confidential computing, especially in the distributed confidential computing scenario. So this is an ongoing research project. So if you have any idea or want to collaborate, feel free to reach out to us. So the scenario we want to focus today is basically a cloud service providing a confidential computing service. So in this scenario, we have these cloud service providers. They may have some TE chips, and they want to provide confidential computing. And our client, in this talk, we will call them reliant party. They have private data, then they want to use CSPs to do confidential computing. So this is our scenario. And of course, when the reliant party use the cloud service, their first question is, or the first problem they have is, they basically has either no visibility or very limited visibility of what's inside the cloud. The cloud service just looks like a black box environment to the reliant party. Like, what if the cloud service provider does not have the confidential computing nodes, and what if they just use the normal machines to provide service? Then immediately the reliant party's data privacy got completely broken. So fortunately, we already have solutions to deal with this problem. We have a procedure called Attestation. So this is a figure from the AMD white paper. On the left-hand side, there is a confidential VM. So the attestation procedure will allow the confidential VM to provide some evidence. We call this attestation report in the middle, together with some other evidence, such as there could be a certificate containing this CVM's public key. And this certificate should be properly signed by the hardware vendor. So this is how we build trust from the hardware vendor to this CVM. So if the CVM just provide all these evidence to the remote reliant party can verify them one by one following some attestation logic. If all the logic is good, then the remote party now can believe that I'm really talking with a legit, secure, confidential computing node. And attestation procedure actually varies based on different hardware vendors, but there are some common practice. For example, they often check whether the certificate of TE is signed by the legit hardware vendor. And meanwhile, they want to check whether the attestation report itself is properly signed. Also, you can basically customize of what you want to attest. For example, you can check whether the firmware version is latest enough, whether the microcode version is good enough. Also, you can check beyond the hardware level, you can also check the software. For example, you can check whether the guest image meets your requirement, what about the software stack. So if you check all of these and all of them pass, you can be convinced that now this TE is very good to use, and it is secure and provided by the legit hardware vendor. And if in the cloud setting, actually, we have two options to get this done. The option one is more like a peer-to-peer fashion. So the TE node will directly send the attestation report together with other evidence directly to the reliant party. And the reliant party basically has everything to verify the report and know whether this TE is good or not. But this actually brings some extra burdens to the reliant party. As we mentioned in last talk, actually reliant party need to track all the golden values, like what's the latest reference values about the firmware, the microcode, and the guest image. And meanwhile, reliant party may have to do some additional computation. So in this way, actually, we are putting more computation burden on the reliant party side. So it may be easy if you just want to attest one TE node. But in the distributed cloud setting, when we say, let's say we may have a lot of TE nodes providing you the service simultaneously, then the cost will become messy very quickly. But the good part of this option is like the trust boundary remains the same. Now you still only need to just trust the TE node. You don't need to trust any other party. So this is the option one. And in cloud setting, we actually have this option too, and in reality, this is more preferred by the cloud service providers. So in this setting, the cloud service provider will also provide a centralized service called the remote attestation service. So instead of sending the attestation report to the relaying party, now the TE node will just send the report to this centralized service, and this service will do all the verification on behalf of the relaying party. And if the verification is good, the attestation service will just send the positive result to the relaying party. And as we know, now there are some hardware vendors also providing this attestation service as well, not in the cloud setting, but the system model are basically the same. So it has many advantages. For example, now it's easier for the cloud service provider or for this centralized service to manage the golden values. And second, the remote attestation service now can be easier to integrate with other cloud functionalities, such as authentication, key negotiation, or token issue. So as a result, this solution is preferred by the cloud service providers, and now most cloud services provide this centralized attestation service. And this actually has a trade-off. Now, the problem is this centralized attestation service needs to be trusted. So the general problem is the trust boundary is expanded. So on the right-hand side, we have the ideal case of using TE where we only trust this TE node. However, now in practice, which is on the left-hand side, we need to trust both the TE node and this centralized attestation service. So it may not be a big problem because most of the time this attestation service is hosted by the CSP, and the CSP are, for most of the time, they are trustworthy. But there are still some corner cases where things could go wrong. For example, what if the attestation service becomes malfunctioning or buggy after some version update? Or now, as an attacker, now you see this system. Now you see this TE might be very secure, but how about just attack the centralized attestation service? Because the security of the system depends on the least secure part. And in our case here, it is this attestation service. So in general, the larger trust boundary means larger risks, and that's not what we want to see. Our goal here is we want to reduce the trust boundary as well. We want to move the centralized attestation outside of the trust boundary. So that's why we call our project Trustless Attestation. And the idea is we want this attestation service to prove to the relaying parties that it is following the correct attestation logic. And this can actually be done by the cryptographic proof. So with the cryptographic proof, instead of just trusting this service, now you can decide to trust the cryptographic proof, or in another word, you can trust math. And the crypto tools we use here is called zero-knowledge proof. So it is a cryptographic protocols, two-party protocols. So one party is the prover, the other party is the verifier. So ZKP, or zero-knowledge proof, will allow the prover to prove to the verifier that some statement is true without revealing any additional information. So to give you some use cases, for example, you can prove that you are a citizen of a country without giving your name or your passport number. And as we know recently, I think last month, Google Wallet just released one of the features for the age verification with zero-knowledge proof, so that you can prove that your age is over 18 without even disclosing your age or disclosing your ID card. So, and actually, zero-knowledge proof has a long history. Like it was first introduced back in 1985, but it got a huge development in recent 15 years, mainly thanks to the blockchain community. So as of now, the zero-knowledge proof becomes very efficient, and it can prove very large circuits. And as we know, in blockchain, zero-knowledge proof is widely used to prove the correctness of the computation. And for example, in Ethereum, or actually in most blockchains, if you want to do some computation on the blockchain, it basically means all the machines hosting this blockchain need to run this computation, and it becomes very costly. So that's why people decide to define some layer 2 solutions where they move some computations off-chain, And in this case, they need to use zero-knowledge proof to verify that the off-chain computation is actually as expected and correct. So it's very similar to our scenario. In our scenario, we just want to prove that the attestation service correctly runs the attestation logic. So it's just kind of a proof of computation. It's very similar to the blockchain use case, actually. And there are many variants of the zero-knowledge proof, and one of the variants is called ZK Snark. Snark means succinct non-interactive argument of knowledge. So it has some very nice properties we want to have. For example, it has fast verification. So the verification is as simple as computing some big number integers and finally do an equality check. So it can be done within 1 second in most machines. And also another advantage is it has constant proof size. So if you use, for example, protocols like Gross16, the proof is simply 3 big integers. And this basically means the communication cost between the attestation service and the relying party will be a constant small number. So our solution here is we want to embed ZKP into the attestation verification. Now we want to ask the attestation service to generate a zero-knowledge proof when they do the attestation verification. And the workflow will be as follows. So there will be a setup phase where someone needs to upload this attestation code to the internet or to the public so that everyone can see it. Then the idea is any party can audit, endorse, or challenge it if they think that this attestation code is wrong. So after several iterations, we will have some version of attestation code that is publicly agreed. And this attestation code will be used for the attestation service. So this is the setup phase. And when the actual attestation happens, the TE node will just send this attestation report together with other evidence to the attestation service. The service will have this attestation code from the setup phase. So this is a version that everyone agrees on. And the attestation service will run this code, and meanwhile, it will generate a zero-knowledge proof, proving that I'm actually using this code to verify this attestation report. So this will generate this proof on the end. So finally, attestation service will send both the attestation result and the zero-knowledge proof to the relying party. And the relying party also have access to this open source version of the attestation code. So he can just use this and the zero-knowledge proof to verify whether this proof is valid or not. And if this proof is valid, it basically means the attestation service is honest. So this is how to enforce attestation service to correctly run the code that you want. And especially when it comes to the distributed confidential computing scenario, actually there are more interesting scenarios. So in these scenarios, we have multiple TE nodes, they collaboratively providing some services. So for example, we may have especially when it comes to the AI use cases, let's say we may have maybe 1,000 nodes. Together, they collaborate to provide AI inference. And in this case, the relying party may need to ensure all of them are legit. So if they just do this one by one, then this means they need to verify the proofs 1,000 times. And also the TE themselves, they need to do mutual attestation to make sure that the TE node that I'm talking with is actually a TE node. Then only if that is ensured, I can send my data to this node. And also in the cloud service setting, there are cloud infrastructures such as load balancer and KMS. So we can also leverage them to do some optimizations. So our goal here is we want to minimize the effort of the relying party. We don't want the relying party to verify 10,000 proofs when they use a service hosted by 10,000 TE node. The ideal case is that the relying party still only verifies just one proof and gets one attestation report, and we ensure that the entire cloud is attested properly. And this can be done by a concept called proof aggregation in zero-knowledge proof. It allows you to verify everything in one shot. So in this figure, you see in the bottom line, there are a lot of single proofs. And in our scenario, those will be the attestation proof for, let's say, 1,000 TE node. And proof aggregation will allow you to aggregate 2 proofs or more proofs into one. And if we do this layer by layer, finally, we will have only 1 proof on the top here. So the idea is if this top proof is valid, it means these 10,000 proofs are all valid. And actually, for different zero-knowledge protocols, zero-knowledge proof protocols, there are different ways to do proof aggregation. And the final proof size could be either constant or it could be increased a little bit, but it will not be, it will be far less than like this 10,000 proofs on the bottom. So also the verification time has the same pattern. And in the cloud service, we have these centralized services. For example, we can use load balancer here. They can play the role of aggregator. In this way, all the TE node can simply just send their attestation report to the load balancer. Load balancer can do the attestation or also generate this zero-knowledge proof. And finally, they can aggregate all the proof together to generate one final proof. So the relying party will only get this one final proof. The task for the relying party is very easy, just verify this single proof. And also mutual attestation also becomes easier since previously without this centralized party, without the zero-knowledge proof, the worst case is they may need to do this in a peer-to-peer fashion. And it becomes very costly when the number of nodes increases. And in our setting, since this load balancer have this proof aggregation, basically every TE node can simply just talk with this load balancer to get attestation done. So this is like, you can think about we are transferring a peer-to-peer network into a star network. And that will save a lot of communication. And also proof aggregation can provide other advantages. For example, when a new TE node joins the cluster, you actually don't need to verify the whole cluster again because it can be simply aggregated to the final proof. So you don't need to regenerate the proof for the existing node. And also, until here, actually, we didn't utilize the feature of zero knowledge because in the attestation procedure, everything are supposed to be transparent. So there's nothing you want to keep hidden. But so we mark this zero knowledge as one of the optional feature. But if there are something that the service provider want to keep confidential, for example, if they want to keep confidential the cluster size or some cluster architecture, for example, their location, then the zero knowledge property could help here. So here we just mark it as optional. We are still figuring out whether there are very interesting use cases where the zero knowledge could be important. And as for the performance of zero-knowledge proof, we actually prototyped 2 versions of this idea. And the general conclusion is the performance heavily relies on the underlying zero-knowledge protocols and the underlying zero-knowledge protocol frameworks. So the first prototype we do is using Circum. So in Circum, you actually need to represent your algorithm as a circuit. And finally, you can use protocols such as Gross16 to prove it. And we have already open sourced this version, I think, earlier this year. And this is our first prototype. And we also implement the second prototype with RISC-0. So RISC-0 is another zero-knowledge proof framework. So the advantage there is like you can write your algorithm using Rust. So this is kind of much better than the for auditability, it's much better than the circuit because it's very hard to verify the correctness of the circuit. So here you can write your attestation logic using high-level programming language, and everyone can just verify it. And then in RISC-0, basically the algorithm will be translated to the RISC-V instruction code, and the zero-knowledge proof is applied on the instruction code level. So we already implement this, and we will open source this version soon as well. as for the performance, since we only want to verify the correctness, so actually we didn't do optimizations. We just want to see whether this will work. So for the Circum version, as you can see, we only tested using our working laptop, it's MacBook. And the proof generation will take like 20 to 30 minutes, so it's very slow. And the proof verification just takes within 1 second, which is still good. For the RISC-0 version, we test the performance using the RISC-0's online proving service. They call it Bonsai. And I think it's hosted by multiple machines with very good hardware. So the proof generation takes around 10 seconds. And the proof verification also takes within 1 second. And proof aggregation will take within 1 minute. So this is the kind of general benchmark we have right now. And as you see, actually, especially for the Circum version, it's not as good. So we did think about if there are any optimizations or other ways to make it faster. And we actually think there could be system-wise ideas. For example, you can use this zero-knowledge proof to bootstrap one machine, to bootstrap one TEE. Then you can use this TEE to serve as the attestation service, so that this zero-knowledge proof verification will only happen one time. So that's how you make the cost lower. And yeah, I think this is basically everything I have today, and thank you so much for listening.
Thank you. Do we have any questions? I've got a couple to start with. You're talking about the aggregation. As I understand it, you're saying that it's close to linear as you add nodes rather than exponential. Did I understand correctly or not?
So the idea is it depends on the zero-knowledge proof that you are using. But for the optimal case is that no matter how many proofs you have, finally the final proof will also have the constant size, which is very small. And for some other protocols, for example, when the number of proofs you want to aggregate increases, at least the size of the final proof will not increase linearly. It will also increase much, much slower so that you can get a benefit.
Okay, so that's the size of the proof, not the speed of the time.
The speed has the same pattern.
Oh, okay, that's not too bad. Thank you. Okay, and the other question I had is very different, which is that when you're proving the code, you're obviously only proving static code, which means that configuration data like golden values, for instance, can't be checked. So presumably in this case, this isn't particularly useful for attestation verification services which have policy, right? Because you can't really check those policies. So it's just for the pure attestation verification measurement.
Yes.
Okay. Can you think of any mechanisms where you would be able to combine those at all? I think that's an interesting set of things to think about.
So do you mean if there are something that cannot be represented as code, or?
Yeah, where you've got policy or being able to have different golden values, some way to aggregate that information with a ZKP.
Yeah, I see. That could be very interesting, since as far as right now, we only prototype things like you check the certificate, you check the signature, and finally you compare the values in your attestation report with the golden reference. And so far, we haven't explored very deep about policies. So yeah, it could be a very interesting direction, and we will need to work on that.
I look forward to speaking to you about it. That sounds very interesting. Any questions from anybody else? This is very interesting from my point of view. Oh, here's one.
I had a general question regarding the P2P versus the star diagram.
Yes.
I think I can see the pros and cons of each, right? At some point, you lose agility. If one node or one T is compromised, then attestation for all the master service will be denied. While there are there are still valid nodes that can be used, but that will render them unuseful, right? So at what stage do you decide that this level of aggregation is the best, you know? Like, how do you optimize between aggregating versus P2P? Because you lose agility, you get more efficient in processing.
Yeah, I think that's a very good view to see this question. And I think in application level, let's say if your application requires, let's say 1,000 TE nodes to collaborate, the idea is, I think in general, if even only one of them get compromised, you should not use this service at all. Even when the other 99, even when all other nodes are good, since this one single node already compromised your data privacy.
We have resiliency requirements of 99.999. So whatever, you have high resiliency, so if it's compromised, I guess I'm trying to think it will become a critical point of failure.
Yeah. I think one of the things that I recognize from this is basically it's a Merkle tree equivalent, right? Where you can cascade failure up and down. It becomes very quickly visible, which means that you can, if you have resiliency and redundancy, you can then swap that in and know very quickly where you need to swap it in. In a peer-to-peer node, of course, the revocation becomes much more complex, although the initial setup is faster. So I think it is a trade-off in terms of redundancy, resiliency, speed to set up, and maybe one other thing. Does that make sense?
Yeah, it makes sense. And as you said, there are two components of attestation. One is just zero-knowledge proof that it is good or bad, yes, and the other is revocation, right? And that becomes, I guess I'm just agreeing with you that this doesn't take care of the other component of revocation, unless you can see on the top which node. Would you be able to see, can you show the diagram, tiered diagram?
So right.
Yeah, so on top of the green box, will you be able to see and swap?
Well, typically in a Merkle tree, what it allows you to do is to traverse the tree very quickly. So you can very quickly find, and I presume that follows in this setup as well, right?
Yeah, it also depends on the protocols that you use. For some protocols, indeed, like if this top proof got compromised, you have no idea which one goes wrong.
That's what my concern. That's
Yes,
what my concern
yes,
is.
that's
If you
a
can
good point.
traverse down, then it's okay. But if you cannot traverse down, I see that as a big critical point of failure risk.
Yeah, that's a good point. I think in that scenarios, actually, we can do a hybrid design. For example, you can compromise some nodes together and do this layer by layer. Yes.
Yeah, build some resilience.
Exactly.
And I think these are some of the interesting research questions that,
that could be interesting.
Working out what the different use cases are like to be. Is it speed of discovery? Is it speed of fixing? Is it redundancy? And they're all different sort of parameters that you can change and say, well, some architectures are better, some protocols are better, some algorithms are better. For those use cases, which is, I think, one of the reasons it's really an interesting set of research you're doing, because there are actually quite a lot of different directions to go in, and it's really interesting to have your question because it comes very much from a business point of view, rather than just from an academic theory. I'm not suggesting you guys are only theoretical, but
this is a very good point. Yeah, thanks.
I'm product manager.
Right.
Thank you. Any other questions? I don't think so. Thank you very much indeed.